So thank you guys for coming. I am very pleased to be presenting here, and I'm hoping that I can share some knowledge with you. My real goal is, in fact, actually to scare you today. That's really my goal. I really want to scare you today, which is why Pakistan is on the title, because as a scientist, I just don't want to talk about the science of things. I also want to talk about the policy side of what science implies for society, and what I do these things in my research, or other people do them. What implications does it have for society? How should we decide things? Science should not exist in a vacuum. Science should exist within society and how people behave with each other. So before I I sort of jump the gun here. My name is Abdullah Khalid. I call myself a quantum information scientist, and I'm currently an assistant professor at Habib University. The other two logos are there because I did my undergrad at LUMS in physics, and I went to the University of Calgary in Canada to do my PhD in physics in quantum information, which is why those institutions are there, are acknowledged there, because whatever I'm talking about here, I learned it at all three institutions. So I just want to make sure that I acknowledge everyone. Okay, so I'm going to talk to you about quantum computing and cryptography, and but before I do that, I'm just going to start talking about just regular computers. Okay, so if you actually go back and look at the history of computers, computers were actually humans. Okay, back in the 1700s or 1800s, all the way up to almost the 1950s. When somebody said a computer, they meant a human who was really good at calculating things. Okay, people would, like, if a scientist wanted some calculations done, or anyone like a finance person, whatever, like business calculation, whatever, they would go out there and hire a person who would do all their calculations, so the scientists would not have to spend time doing tedious multiplication, addition, and whatnot. And so, for example, there's like a picture of 1700 of a computer who was actually calculating when the Halley's comet was going to return, which is sort of one of the earliest problems that was sort of showed what Galileo and all of his contemporaries, Newton and Galileo's theory about Earth and gravitation and the solar system was all true. So those calculations was done by this gentleman who was hired to sort of just calculate numbers all day long, because next to that is some instructions for a computer, so these days we write code and stuff, but back in the day it was just a sheet of paper, do these calculations, this, and just give me the answer. And this continued all the way up to the 1950s. This is a picture from the United States in their some aeronautical or something or similar department, where there were these people who were just hired to just calculate things. So this is sort of the history of where computing came from. And then, if any of you have seen the Alan Turing movie Imitation Game, you might know that to break the Enigma machine, he built this mechanical computer. Okay, it was not an electronic computer made out of transistors and stuff. It was actual wheels and rods moving around and calculating things. And this was all happening in the 1940s. And eventually, we ended up to today, where we have our laptops, and they are supercomputers hidden away, and there's an enormous amount of computing power available across the world. If you just put them together, it's unthinkable how much computing power we have, and we just compute all day long with all these computers. Okay, so there's a number. I don't know if I can give you an intuition of how big that number is, but it's all the computing capacity of all the computers right now in the world. So let me talk about just what computers are. Okay, so computers are what they solve computational problems. Okay, that's what we do with computers. Okay, that's sort of their goal. And the simplest computational problem that you can think of is just multiplication. You have two numbers, and you just multiply them, and you get a number result. And we all learned the grade school method of of multiplying two numbers and getting an answer. So you have a problem, and then you have an algorithm that a grade school kid can sort of follow through and sort of get the answer to. Of course, you can also sort of write a code for it. I'm sorry, the resolution of this is not as good, and I thought this would be visible, but I guess not. So, but there's some code here, and you can run this on a digital computer and sort of get the same answer so the point is that for the same problem, which is multiplying two numbers, you can use two different machines, one a grade school kid or an electronic computer, and sort of get the same answer. And the two machines might be following different algorithms. The algorithm that the grade school kid follows is not the same algorithm as what the computer is doing. It might be doing different things to make it easier or faster or whatever. It's, like the computer would sort of exploit its powers where it's good at, and the grade school kid will exploit what their limitations are to make sure that they get the right answer as fast as they possibly can. Okay. So the other problem that I want to think about today, and I'm not just introducing multiplication and factorization just randomly, you'll see that they'll appear again in the talk again and again, is the opposite problem of factorizing numbers. So imagine you have a big number, or well, any number, say for example 21 is right there, and if I ask you to sort of factorize it into its prime factors, you would say 7 into 3, where 3 and 7 are factors, okay? But if I gave you this ginormous number with 12 digits, and I asked you to sort of tell me the prime factors, it's just a multiplication of two prime numbers, okay? And that's the result. If I told you, I don't think anybody here has any idea how to calculate it. What you would probably do is start with 2 and see if this number is divisible by 2. If that didn't work, you would try 3, and if that didn't work, you would go to 5, 7, 11. You go through all the prime numbers and keep going till you sort of hit a number that divided this. And if it did, you were good, and you would have found the two factors. Otherwise, you would you would keep going. So factorization, so multiplication is a sort of easy process, and it's very easy to do either by hand or on a computer. Factorization is still hard for both humans and computers. And here are some of the different algorithms, like I just put names, and you can put those algorithms in a computer and sort of try to find out how easy or difficult it is. So let's sort of try to quantify this sort of difference. So what you can do is, what I had here was sort of the number of digits of my number. See, so 21 had 2 digits, and the bigger number has 12 digits. You can sort of have the number of digits on the x-axis, sort of try to quantify how difficult it is to solve the problem, the best possible way of solving the problem. And multiplication is easy. Well, depending on how you count, it's sort of like the amount of time it takes to solve multiplication is not that much. So if it's a 12 digits number, it will be proportional to either, well, usually depending on your algorithm, 12 square, which is like 144. So it might be so if you double your size, it will only go up by a factor of 4. But if you want to factorize, it actually goes up exponentially. It sort of goes away. So pretty soon you are dealing with numbers of times of factorizing numbers, which is really, really high. And it becomes very difficult to factorize numbers, and all the computing power, it's very easy to write down a number, like a big number, which is a multiplication of two prime numbers, which all the computing power in the entire world could not solve, even if they spent tens of millions of years or billions of years trying to do so. Okay, so let me just take a slight detour and talk about cryptography, which is sort of another thing that people who sort of deal with computers and all that jazz do. Cryptography is where you try to so there's Alice and there's Bob, and Alice wants to talk to Bob, but there's Eve who's trying to listen into the conversation. Okay, and the way Alice and Bob don't want Eve to listen to whatever they're saying, so what they do is sort of they encrypt their message and then send it along, and Eve can, so even if whatever the top secret info that Alice was trying to send to Bob, she would encrypt it using this key, which is sort of this mathematical process, and it would get converted into the ciphertext, which would be gibberish essentially. But Eve would try to try to listen into the conversation, she would just hear gibberish. But Bob would also have the key, so Bob would be able to recover whatever Alice was trying to say. And cryptography is sort of one of the entire bases of our modern technological civilization. The information age is based on cryptography. If we don't have cryptography, we don't have any of the information age things that we have. We would be very stuck in doing very basic things, because security is essential to a lot of human activities. So for example, if you just want to talk to your bank, log into your bank account and do a credit card transaction, or just transfer money in the bank account, that requires cryptography, so people can't steal your money. If you want to just log into your email, into Gmail, or into Facebook, or whatever, Instagram, Snapchat, whatever, that requires cryptography, so other people can't log in and either post on your behalf, or send emails on your behalf, or read whatever your emails are, anything like that. And obviously, cryptography is obviously used for more serious things like military communications between, which is also very important. And so it forms this basis, and there are various ways of doing cryptography, but the prime way of doing cryptography that we do today is what is called the RSA encryption protocol, named after these three British gentlemen, Rivest, Shamir, and Edelman, who came up with this procedure of what Alice and Bob can do, this mathematical procedure that Alice and Bob can follow to ensure that Eve cannot listen to their conversation. And the rough idea, so it's called the RSA encryption protocol is a very clever idea, essentially, where what happens is that if this is Bob, and what happens is that Bob has this mailbox that only he has the key to. And what Alice can do is, if physically speaking, if Alice drops a letter into Bob's mailbox, nobody can read the letter that was sent to Bob, because because they can't break this unbreakable or very difficult to break mailbox. And unbreakability of and obviously Bob can listen and read whatever Alice sent him by just opening the box with the key and taking out the message. So the process of putting the envelope inside the box by Alice is called encryption, and that is just essentially in the RSA protocol is just multiplying numbers. It's very easy to do. And equivalently, Bob opening the box with his key is just called decrypting the message, and it's also just multiplying numbers in the protocol. But for Eve, who's trying to crack the code, who's trying to listen to the conversation, actually trying to break the box somehow, to try to sort of open the box in some nefarious way and trying to read Bob's messages, would actually require Eve to factorize numbers. Okay, so essentially, what you have is that you have some key, which is essentially this string of digits, and the security is proportional to the number of digits, because you just make the key so long that Alice cannot factorize the key anymore, and it's very difficult for Alice to read what Bob is doing. Okay, so here's sort of obviously they can be, and sometimes it can be. So just to give you an idea, people have been trying to crack RSA and sort of see how secure it is, and in the 2010s, people can break any encryption system where the number of digits of your encryption key are 768 digits long. So this was in 2010. You can obviously do 10 years later. We can do a bit better, but essentially the current, I don't know if I have it. The current recommendation is that if you have 4,906 bits, people expect that even with the increase in computing power and all the advancements in algorithm research and all that, whatever you're communicating with will be secure till 2030s. And if you want to be secure for even longer, you can just increase this to 8,000 or 16,000 or 32,000 bits long, and just it's very easy. It doesn't really cost too much these days to just increase the key size to whatever you want and just secure it for a long time in the future. Okay, so that was encryption and cryptography, and I now want to talk about what I just established was that on a regular computer like this or on a supercomputer, it's really difficult to break encryption, because you have to factorize numbers, and that's really hard. Now, in comes in quantum computers, and I now want to talk about quantum computers and its basis, quantum physics. So I'm sure all of you are familiar, back in the day, Newton and Faraday and their friends and everyone else, had this conception, this framework of sort of analyzing the world that was called classical physics, F equals to ma, the electromagnetic equation, Faraday's law, the equations of thermodynamics, the second law of thermodynamics, entropy increasing, all that jazz is all classical physics. And but people found out in the early 1900s that that description of the world was incorrect. It did not predict for various things. And some of these gentlemen and other people, obviously, a lot of hundreds of other people came along, and they came up with this new theory called quantum physics, which was able to describe a lot of things in our universe. So just to sort of like give you a rough overview, whatever that Newton and his friends did was called classical mechanics or classical physics, was all about things which were large by, things about roughly human size, or like, things we can see, that sort of thing, and they were always moving slowly. Quantum mechanics was all about things which were really small and not moving really fast. And of course, if you start to increase the speed, you get relativistic things that Einstein did, or quantum field theory, which was even a later development. But we just need to restrict ourselves to sort of this quadrant, where we're looking at things like really small things, like atoms. How do I describe the behavior of atoms, of molecules, of just electrons, bare electrons, or even just large materials, like, if I want to describe the properties of, for example, this light bulb, I sort of do have to use quantum mechanics to do it properly. Okay, so I just described the computational problems. I described two computational problems before, which is factorization and multiplication. Let me now introduce another computational problem, which is the problem simulating physical systems. So I want to simulate atoms, molecules, and materials, which means that I want to find out how these things behave. I want to know how what happens when if I shoot light at an atom or a molecule, what happens to the atom? Does it shoot light back, or what does it do something else? When does a material break? When does it, if I want to melt a material, what is the temperature at which it melts? These are all simulation problems which are called just simulation of physics problems. And all of these laws to describe how atoms, molecules, and materials behave were all known by the 1920s. But what people realized, Dirac, for example, who was one of the originators of quantum physics, he realized was that all the underlying laws, physical laws of physics and the whole of chemistry are all completely known. Like they knew, like they could, whatever experiment they did, like the result of the experiment agreed completely with the theories. But whenever you tried to do anything very complicated, if you tried to do a difficult problem, it was really hard to simulate it, to sort of calculate the equations and to get a result was really, really hard. So he said this in 1929. So I just want to just point out, okay, this is from the era of human computers, when people, still humans were calculating things, okay? 1929, there was no such thing as a digital or a mechanical computer even then. Okay, so this problem sort of continued all the way through the 30s, 40s, 50s, 60s. People came up with these electronic computers using the transistor, using the solid state transistor, and they tried to simulate molecules and atoms, just simulate physical systems, and they found out that it was really, really hard. Like they could not make any progress. And the reason was that the equations of quantum mechanics were really difficult, are really complicated. They explode. There are a lot of variables, and you just can't do it on a computer. It just runs out of memory very fast. And all the way in 1982, this is almost this 50 years later, after Dirac made a statement, Feynman sort of gave this. Who was a very famous physicist. He said that well, if nature isn't classical, nature is quantum mechanical. The physical theories that govern our universe are quantum mechanical in nature, and if you want to simulate nature, you can't just depend on a computer that is classical in nature, that uses classical physics. You want a computer that is quantum mechanical in nature. Okay. What does that mean? That means is, okay, the computer that we have, this computer and the computer, the human computers, they are not exploiting the full laws of nature. They are sort of using the laws of nature that Newton and his friends thought, the old laws which are mere approximations of the true laws of physics, which is quantum physics. And which is why it is really hard. You have to use quantum mechanics. So I'll try to explain to you in this sort of this analogy. in this car analogy. So you can think of like the computational problem, like factorization, multiplication, or simulating atoms is as going from A to B, okay? That's a problem, like that's a physical transport problem. You just want to go from point A to point B. And a slow car can get you there, and a fast car can get you there too. And so can a helicopter. But they're all different things. The difference between a slow car and a fast car is just a quantitative change. You made the engine slightly better, you used slightly better material, you made the engine slightly bigger, you improved the aerodynamics of the car and things like that. And you got this quantitative improvement. And there's sort of a limit to how fast you can make the fastest cars. Okay? And in our analogy, that is of computers, the slow car is like a human computer, a digital computer, or a computer from the 90s, a Pentium, or even this computer. And you can make it faster by sort of building more of them and sort of making sort of local improvements to it, and making a supercomputer. But it's still using the same laws of physics, so it's only a quantitative improvement. What you want is a qualitative improvement where you, instead of like thinking completely out of the box, instead of thinking of cars, you start to think of the air and you invent the helicopter, okay? Which also solves the same problem. It takes you from point A to B. Anything that a car can do, a helicopter can do, and anything that a helicopter can do, a car can do. It's just the speed at which all of these things are doing it. And obviously the helicopter can do it a lot faster. Like a fast helicopter is much faster than the fastest car, okay? And obviously, like you can think of an aeroplane, which are even faster, like many times faster. So there's this qualitative improvement, and that is what a quantum computer is. It's a completely different way of exploiting the laws of physics to do computation. So to sort of make it more concrete, what Feynman said, and this is roughly what he said. Suppose you want to simulate this big blob of like molecules, maybe it's in the body or something like that, it's a drug or it's a protein, something like that, and you want to simulate it. What you do is, like you can't make a classical, if you make a computer like this and try to simulate the results on that computer, it's going to be slow. What you do is you do this. You take some atoms and put them in well-defined positions, okay? And so they're all put on a grid. And then you sort of control the interactions between the atoms. You control it precisely and accurately. And you control them in a way that the interactions between these atoms reflect the interactions between these atoms. So, and these atoms are governed by the laws of quantum physics, and these atoms are also governed by the laws of quantum physics. So what you can do is, by meditating the interactions here and making it behave like this, you sort of let it evolve from some time, and then whatever properties this had, this would also have the same properties. And then you can measure it and use that to just, get the properties. That's the shortcut. That's what makes it easy. Like you sort of use quantum mechanics to simulate quantum mechanics. Okay? So this was Feynman's ideas. And sort of that led to this revolution in the physics community, in the computer science community, because people thought, nobody had completely thought of this before. So, well, actually there was a Russian scientist who had thought of it 2 years earlier than quantum, Feynman. Feynman said it in 1982, there was a Russian scientist who said it in 1980, but he wrote it in a very boring and bad journal and nobody ever read it. And like somebody discovered that paper 30 years later and said, oh wait, he said it before, but now in history books everybody says, because Feynman was the one famous one, he promoted it a lot, so now everybody sort of attributes it to Feynman. But anyway, people started working on it, and there was a lot of work that was done and trying to understand whether you could build like computers like this, which were sort of like this, and there was a lot of money poured into it over the years. So here's sort of the map of what was the state a few years ago in 2015, where the total world estimate of research sort of investments into quantum computing is about 1.5 billion euros, okay, which you can realize is a lot of money, okay, and China is was in 2015 was plugging in a couple of million, United States was plugging in a couple of million, the European Union was plugging in 550 million, and these are figures from like a few years ago. Like right now, like it's the number is like several times that. Like it's probably each of, like United States is probably plugging in 1 billion every year. So is China. So is the European Union. There's this race of building quantum computers, and I'm going to tell you why everybody's really trying to build quantum computers today. So Oh yeah. So just to sort of complete the story, that like starting from Feynman in 1982, what we have today is actual quantum computers that you can play with. So if you go to the IBM Q Experience website, you can sign up and write code that will be sent over the internet to IBM's computer. And I think I had a picture of that a couple of slides ago. This one. So on this computer, and it will be it will process the data, whatever problem you're trying to solve, and will output the results. It's a very small computer. You can't do anything useful with it, but you can do it. And in fact, just this week, like there are people at Google who are trying to build a quantum computer, who sort of this paper was sort of leaked. It's not peer reviewed yet. But somebody leaked the paper that they were writing, where they showed that they had built a quantum computer that could solve a particular computational problem. I'm not going to go into that, much faster than any classical computer ever could. Okay? So like this week was a sort of a milestone in the history of quantum computing, where where somebody was able to build a quantum computer. So the IBM Q computer, everything you can do on this, like I can write some code on my laptop which would sort of do the same thing very fast, and like the IBM Q computer might take a few minutes, my laptop might take a few hours or something like that, or maybe a few days. But the Google computer, which just came out, is able to do computations that you put all the supercomputers, all the computers in the world together, and they sort of do it. And even it would take like millions of years for them to sort of do the same computation, and it was able to do it in 200 seconds. I don't think you can read it. So they sort of showed, okay, they have a computer that is much faster than anything that we can build with classical techniques. Okay, so before I sort of go on and tell you what quantum computers can do, I want to talk about what quantum computers cannot do. Okay, this is very important because I see a lot of media articles, I see stories, and I'm sure some of you have read those stories or heard those things or heard casual discussions about this, and they talk about all of these things that quantum computers might be able to do, and there's a lot of inaccuracies in that. So I just want to establish, and before the hype gets down, I'm going to quash it. But I'll bring it up again in the right way, where I want to say that like the really hard problems that it's really hard for classical computers, which are called NP complete problems. I don't know if there's computer scientists here. Like things like doing industrial optimization, predicting the stock market, optimizing airline schedules, predicting the weather, I don't know, doing other things like this. All of these problems quantum computers cannot do. Okay, they will be just as bad at them as classical computers, because the algorithms we have written for quantum computers, we don't we don't really expect them. Like even though we haven't proved that quantum computers won't be able to do it fast, but we don't really, like, based on what people have sort of researched and they understand of the systems, we don't think this will ever happen. And the other thing that people sort of say about quantum computers a lot is that they're sort of, you know, they can do these things because they're computing all the computing or calculating all the answers in parallel, and that's completely false. Like quantum computers can, like, sure, in a certain way they do some sort of parallel computation, but then you also have to measure the state of the system, and that measurement is a random process. So you can't sort of use this parallelism to solve every problem. Only certain problems where you can sort of get things right is where you get the sort of speed up that I'll show you. So the speed up where quantum computers do shine is that they can simulate atoms, molecules, and materials the same way Feynman conceived of, exponentially faster than classical computers. And you know, that means like drugs. So the practical effects on society, that's what I want to talk about, is that you can do things like you know, drug design. Like right now, if you want to design a drug, what you do is you do thousands of trials with like test compound after test compound with slight variation, you know, doing it again and again. And the reason is because simulating the medical drug is really hard on the computer. So obviously then you have to do the experiment and sort of see what the result would be of putting the drug into a human body. So, but if you have quantum computer, you could sort of simulate, you can simulate it faster and quickly on the quantum computer, and you could sort of cut out all those thousands of trials from your drug delivery research timeline, and then you could do all of these things much faster. I don't know, the cure of cancer could be hinged on someone using the first quantum computer to sort of run some simulations and figuring out how cancer cells behave. You can also, like other things like solar cells or other materials that people work on, like all the advancements, technological advancements that sort of make the comfortable modern life possible, can also happen because of our ability to simulate atoms and molecules instead of just sort of testing them out one by one in the lab. The other thing is that quantum computers may be able to do machine learning and optimization. So I put a exponentially faster than classical computers. I put a maybe because people have come up with various, this has happened a few times where people have come up with this really fast way of doing machine learning on quantum computer, and then somebody says, oh wait, you can actually do this just as fast on a classical computer. Like they sort of get inspired by the machine learning algorithm on the quantum computer, and they build a similar algorithm on the classical computer that does just as fast. So it's sort of a maybe right now. People are still working on it. It's a really active area of research, and it's happening. Maybe it will turn out, maybe it won't. The big thing, obviously, as you might have realized, because based on my discussion of encryption and cryptography before, is that quantum computers can break encryption, can break the cryptography that we use to fuel our information age. Any asymmetric encryption protocol that we use today, all the major ones, they're all breakable by quantum computers. Whoever builds the first quantum computer will be able to steal all your money, will be able to read all your emails, the military communications, like government secret communication, whatever, any secret communication that is happening in the world with the right, like you could tap into the right cable, like read the ciphertext and sort of break it and crack it using a quantum computer. So quantum computers are extremely dangerous. Like I just told you a really good thing about quantum computers, like drug delivery and all that medical advancements. But there's also this really dark side to quantum computers, is that they can break the very basis of our modern civilization. Okay, so building a quantum computer, like, and I showed you that people are plugging in a lot of money, like billions of dollars every year, into trying to build quantum computers. So, and this is sort of the reason, like there's no internet, like nobody, like nobody's going to the UN and saying, like we'll all stop building quantum computers till we figure out this problem. What happens when somebody builds a quantum computer and they can break all encryption? It's just a sort of this race going on, similar to the nuclear race, where like China is trying to build the quantum computer faster than the US is trying to build it faster than Europe is trying to build it faster than India. India is not, like, I don't know if it was there, India is also plugging in a lot of money. So like Japan is plugging in a lot of money. Everybody's trying to plug in money and trying to build a quantum computer, and whoever gets there first is has this huge advantage on the human society scale of how things are done. Okay. So just to sort of put these things in graphical things, so before I said, if you remember my graph from before, I said that factorization was difficult on a classical computer, and that is the same thing as breaking encryption on a classical computer. Cracking encryption was exponentially hard. But on a quantum computer, if you want to break encryption on a quantum computer, it just becomes easy. It's a polynomial in the size of the problem. Whatever your key size is, it won't be very difficult to break it on a quantum computer. This is what this graph is showing you. And as I said before, on the cannot do slide, there are some problems that are really difficult on a classical computer. A lot of problems that we deal with daily life, they're difficult on a classical computer, and they're equally difficult on a quantum computer. Okay, so like sort of they will all blow up exponentially, and like it's still difficult to do them both. But certain problems, here also you have the simulation of atoms, here you have the machine learning applications, maybe all of them going on here, which are easy to do on a quantum computer. Okay, so I just want to sort of, this is the sort of the list. I just want to list all the cryptographic algorithms that we use. So there are two types of them. There are the symmetric key algorithms, and there's a public key. And all of these public key ones, RSA is the most prominent one, are no longer secure against quantum computers. Okay, these are mainly what we use. Like if you can't use them, like these ones, the symmetric key ones, which are sort of not really impacted too much by quantum computers, you just need to increase your key size. They're impacted, but you can just increase your key size. But they sort of depend on these guys to sort of work. Like you can't really just use them in isolation. You have to sort of use these together. And because these are broken, like all our essentially cryptographic communication techniques are sort of broken. Okay, so if people are building quantum computers and they're going to break their encryption, what do we do? Okay, we also have to start thinking about what we should do to sort of ensure that our communications remain secret. And there are sort of two ways of doing it that we know of yet. Well, the third way is obviously to tell everyone to stop making quantum computers, have an international treaty, stop. But I don't think that's going to happen. So the two technological solutions to this are one of them is post-quantum crypto algorithms. Okay, they're just called post-quantum because people claim that some of these algorithms are secure against quantum computers, that quantum computer would not be able to break these encryption algorithms easily, like it will be difficult. The problem is there's no proof. Like people sort of, there's guesses, there's a lot of conjectures, a lot of assumptions that go on, and people have developed them. Like it's probably a good idea that we shift to these guys, we start using them instead of the ones that I showed on the previous slide. But there are no proofs of security, but there's hope that they will be secure, and all we have to do is sort of agreeing on new standards for encryption, because it's sort of an international effort. Like you can't, like I can't start using just new algorithms and that can be the end of it. Like communication is a two-way street. Like if I want to talk to someone in the US, I have to also convince them that they have to use these algorithms, and I use them and they use them, and then we can sort of communicate. So there's this whole effort going on right now to convert the world's encryption standards to these post-quantum crypto algorithms, and I think the goal is to sort of get a good chunk of the communication by 2025 or 2030 onto these new standards. But there's a lot of discussion, there's a lot of fighting, not sure what will happen. Obviously, like organizations like NSA, who are really interested in not letting people encrypt their content, are obviously trying to stop the standards from developing, and they want to be the people with the quantum computer who can break into everyone, and nobody uses post-quantum. So there are all these political problems that are there with post-quantum crypto. The second option is quantum key distribution, where thankfully what happened is people discovered, and this is just 2 years, in 1984 was the first protocol somebody thought of, like completely independently of Feynman. They hadn't even heard of Feynman, I think. Like Feynman's talk about quantum computers. They figured out a way of doing this encryption way, of replacing public key encryption systems with this thing called quantum key distribution, where the goal is that Alice and Bob sort of send light to each other, photons to each other, in very special ways, and then they measure them in very special ways, and based on that they sort of get this secret key. And the thing is that Eve can sort of like listen into whatever like Alice and Bob are doing with their photons. She can interrupt, she can try to read what the photons, the state of the photons is, but the proof of security is that no matter what Eve does, Alice and Bob will be able to find a secret key that Eve does not know of. And what you can do with this, what you can do is, what I said before is, where did my table go? Yeah, these guys, which all these algorithms are used currently, so sort of instead of using these broken algorithms, you sort of use quantum key distribution, and plus you use these symmetric key algorithms, and together those two things are secure. So this is sort of, I have this graphical representation of this. This is the part of so Alice and Bob want to talk. This is the encoder and decoder, and this is the part which was used by RSA to currently used, and you sort of replace it with quantum key distribution to get a random secret that Eve cannot find out, and then they use the symmetric key algorithms to talk to each other, and all of this is provably secure against quantum computers, both against classical computers and quantum computers. Whatever you do, this is really hard to, like, this is almost impossible to break. So if you do it all right, you're all good, and you can do secure communications again. So there's hope. So just because people can build quantum computers, there are these two options where you can either build you can either build these like shift to post-quantum crypto algorithms that run on classical computers, or you can start to build this infrastructure for quantum key distribution, which will help. And you can actually just buy these. These are like quantum key distribution. While quantum computers are still sort of in the infancy, and maybe we are like 5 to 10, maybe 15 years away from actually building like quantum computers that can break encryption. Quantum key distribution is already available today. You can go out there to QBTech's website and sort of order these boxes that can allow you to do secure, do this quantum key distribution stuff. And I haven't researched these prices in a few years, but like, and sort of depends on your particular applications, but it's not that expensive. Like these boxes cost like a few $1,000s to, you know, a few $10,000. But obviously as people start to buy more of them and they become, like these are built by hand these days, but obviously when people start to build them at an industrial scale, these become very, very cheap. So that's the other way. Okay, so I am now sort of at the end of my talk, and this is where Pakistan comes in. You know, so obviously we have no money. We have no money to educate the people in our country. We have no money to fix the roads in Karachi or provide water. Obviously we can't plug in the billions of dollars to build a quantum computer. But what can we do? Obviously the first thing is, like, we do have money, so we should be investing in quantum computing and cryptography research. As far as I know, there may be like 5 or 10 people right now in the country who sort of understand these issues to any significant extent, which is like a laughably low number compared to, you know, there were 5 to 10 people in the university where I did my undergrad who understood these issues at the world-class level, like full profs. So obviously you need more people in the country who sort of understanding these issues, the scientific research, so you sort of build the technical know-how to sort of deal with the technical challenges. And I think we should also start considering building quantum cryptography infrastructure, you know, just to start testing things out, see what we get, you know, just building these things will sort of help inform like whatever, like sort of help our security in the future. And obviously we have to sort of do the policy research. Like obviously I just gave this talk, but like, you know, somebody needs to sit down and do write down a white paper about how Pakistan should deal with these challenges properly in the future, you know. And obviously there's all these international encryption standards that everybody else is a participant of. Pakistan is not a participant of them, as far as I know. I sort of I sort of read those mailing lists from time to time, and I've never seen a Pakistani name ever there. It's all, you know, American and Canadian and European names. There you never see Pakistani, so you sort of need to sort of, you know, invest in the research part and then get those researchers start participating in the international standards committee, so we can sort of have a say in the international scale of how these things are done. So, you know, we sort of ensure that our interests are talked about at the international scale. So I am done. I think that was the end of my talk. So I will, oh, thank you. So I think the floor is open for questions now. Okay, like maybe we can go there and then we can go there.
Could you elaborate on what do you mean by quantum cryptography infrastructure? So what sort of infrastructure?
So the quantum key distribution. So we have to, so to build the quantum key distribution, we need to lay down these fibers or launch satellites. So satellites are really expensive, but you can probably lay down fibers between, you know, all the major cities to sort of send photons using these boxes between cities, between different institutions, between universities, between, you know.
Same fiber optic?
It's not quite, it has to be better standards. It has to be a lot finer. It's like the fiber optics that we use for our internet or TV has, like, every pulse that goes in there has sometimes hundreds of thousands of photons. We have to go down to the single photon level. Every pulse has to have one single photon. So that's sort of the infrastructure we build. So it's obviously a lot more expensive. Yeah. Yes, so you had a question.
Firstly, I really appreciated the lecture. That was really informative. I missed some of the beginning, but and I don't know if that, like.
Is that on? I don't think it's. Okay. I can hear you, but I don't think they wanted the video to record it. Your question. I'll repeat your question.
But basically, my question is that, like, the advantage of quantum computing, right? Like, how does that help us, like, be able to solve encryption that much quicker? Is it because of, like, just the fact that, like it's quicker, or, like, can you just, like, elaborate on the on the how part of it, like how is it like better at decoding those encryptions?
Oh, okay. So, as I understand, the question is, what do quantum computers do that make it better at breaking the encryption, right?
Basically, yeah.
Okay. So that's a very good question. I don't think there's a short answer to it, and a reason why I sort of did not try to squeeze it into my talk, because as one of my students is here, he would attest, we have been sort of struggling with these concepts for over 2 months now, and we are still not there.
Right.
It's like, because to explain quantum computing, you have to first explain quantum theory, and that not just sort of a set of equations, the whole philosophical framework.
But you, just to interrupt there, you can talk to me with as someone who is like a hobbyist in the sense, like I am pretty informed on quantum concepts, so
okay.
You can feel free to.
So the algorithm that is used by quantum computers to the procedure that is run, the code that is run, is called Shor's algorithm, named after Peter Shor, an English mathematician who sort of designed this algorithm to factor numbers really fast.
Okay.
So the way it does work is, in a way, it does calculate all the answers in parallel. It sort of checks all the factors of a number in parallel, but there's a whole trick to it where it ensures that the probability of, like, when you measure the outcome, the probability of getting the wrong factor out at the end is essentially 0, and the probability of getting the right answer is almost 100%. So,
okay, I see.
So
that's solely due to the algorithm itself, right? Like the ingenious is in the algorithm.
It's the ingenuity of the algorithm itself, but it's also the structure of the problem. Like factorization, there's some sort of structure within numbers, within how prime numbers are distributed and how they relate to other numbers.
Okay.
And that structure is sort of exploited in this algorithm. So the reason that NP complete problems are not solvable fast is that, as we understand, there's no structure to the problem. There's no reason why when you try to schedule, optimize the scheduling of your airline flights or airline flights, like routes and stuff. There's no structure to the problem. There's no reason why any particular solution would.
And that's because it's essentially non-linear in nature, right?
It's a non-linear process, but it's it's a structureless process. Like there's prime numbers are sort of very special in numbers. So so when you try all the answers in parallel, the prime numbers sort of drop out of and you get the prime factors correctly, but it doesn't work for NP complete problems. So that's sort of the reason. Maybe the next question.
Thank you so much.
Yeah, no problem. Yeah, there's a question right there.
Yeah, thank you very much. It was wonderful, but I was totally a layman and zero technical background.
Okay.
So it was interesting that I have seen your final recommendation for the government of Pakistan.
I'm sorry?
Your recommendation for the government of Pakistan, you have mentioned that we should advance
absolutely.
For the research and go into the quantum computation system.
Right.
So what I have understand that it is the evolution of the computer from mechanical to electronics, and now we are moving toward the quantum computer system.
Absolutely.
So it is more advanced, and it is more secure.
It's the quantum computer. The computer itself is not secure. It's the It's the.
So for my question, not but request is that for a layman, my background is with the sociology. So for a sociologist, what is your message?
My message is that we need to secure ourselves in a future where quantum computers will be used, because our encryption will be broken. That's the thesis of my talk. Encryption that we use, all the security that we use today, is going to be broken. We need to figure out a way of ensuring that in the future, in 2030, we communicate in a way that is not breakable by a quantum computer. That is what we have to do. There's no other option. There's a question there, and I think there was a question there.
Hi. So you said that it checks for all answers in parallels. So are we looking at all the possibilities, or is there a right or wrong? I mean, I don't know.
So if you try to factor 15, for example, okay? So you know the factors of 15 are 3 and 15, okay? Well, let's try a bigger number. Maybe let's try 21. So 7 and 3. But there are all these other factors that, like 5 and all the other prime numbers, 2, 5, 13, 11, which are smaller than 21, which could be factors of 21. And it's sort of like, but it's a very subtle process, and it sort of ensures like the process runs, it sort of checks all the answers in parallel, but then there's this step additionally which sort of like, so you do this computation and then you measure in the quantum computer, and then the result of the measurement is random, okay? So if you just try all the answers in parallel, which is very easy to do, it won't give you the right answer. You have to do this additional step where you sort of ensure that all the wrong answers have 0 probability of coming out right, of being measured, and all the right answers have like 100% probability of being measured. So I don't think there's an easy way of explaining this, so which is not why it's not there. Maybe you should. Are you a student at Habib?
But I'm from the social development policy.
Okay, so maybe I might be able to offer a course on quantum crypto which has 0 math in it next semester. Maybe you can take it, and then we can talk about it.
So my question is, what makes it secure or more secure than the traditional techniques, the traditional computing?
Quantum key distribution?
Yeah. And the second thing, which is related to it, that if the thing is the performance which makes it secure, like the computations are higher than the traditional ones, then is there any possibility that this can be decrypted, or in future the possibilities of that?
Good question. So okay, so I'll talk about the first question. The first question was, how does this why is this secure against sort of future advancements in computing? So the reason is that well, all you're doing is secret key. So like Alice is here, Bob is here. Alice like shoots shines a laser at Bob, and Bob sort of detects what the laser is shining at. So she can send it in different ways. So if you understand, I don't know if you're a scientist or like if you have a science background, you understand that light has a polarization, which is sort of the rotation of the light. So the laser light is not just a laser light; you can sort of rotate it, and like this is what is depicted by the different rotations here. So when Alice shoots lasers at Bob, he can sort of detect what sort of polarization of that laser was. And the reason it's secure is that whenever Eve tries to measure or tries to disturb the photons in any way to sort of figure out what Alice is doing, Bob knows. Bob figures out afterwards when they sort of afterwards that Eve tried to mess with the communication channel. So then they sort of discard those shots of the laser, and then they start again. So Eve cannot do it. Like whenever Eve tries to disturb the system, Alice and Bob will be able to detect Eve was disturbing, and then they don't use that computer. So Eve can do nothing except, like she can permanently block it, that's totally okay. But if she decides not to block it, then Alice and Bob will get the secret key that Eve has no information about because she was not able to disturb it. And this is secure because this is completely random. Eve has 0 information about this. Like in the information theoretic sense, Eve cannot know anything. She has no idea. If you ask her what this bit is, she will say 50% chance is 0, 50% chance is 1. Like she has no more information than this. And what you can do, if you know any computer science, there's a one-time pad.
Sorry to interrupt you.
Yeah.
As in the traditional encryption or decryption technologies or techniques, there's a sort of combination sort of things.
Right.
Like the probabilities or combinations are being used. And for the high-speed computers, there's like the quantum sort of things,
right.
sort of computing structure or architecture has been used. So is it possible that thing should be decrypted, can be decrypted in future? Or
no, absolutely not. Like this is provably secure. Like this is, like if you use if you use the secret key which Eve has no information about, and you use here a one-time pad, there is 0 information that Eve will ever gather about it. No matter how much computation power she uses all the atoms, all the galaxies in the universe to build this giant computer, and she will still not be able to find out what Alice and Bob are doing. It's that secure. Like there's 0, like it's a ironclad proof.
And the special way in which they're communicating is predetermined, right? So the laser.
Absolutely. There's this.
They both agreed upon a certain set of principles.
Absolutely, there's a whole protocol for doing it. Yeah, it's not very difficult, so which is why those boxes are very cheap.
All right,
there were more questions.
Apart from like drug modeling and drug design and cryptography, etc., would quantum computers have applications like business side, like data mining, business intelligence, or even artificial intelligence, things like that?
No, probably not. Like that's the whole
Yeah, I think
like I had this whole slide. Everything which is like all these business problems, all these like all these commercial problems, a lot of these, they are difficult for classical computer, they're difficult for quantum computer. Yeah, so like it's not like, so in this analogy, there was a very particular reason I had this helicopter analogy where which I failed to mention is that everybody uses cars, okay? Almost everyone uses cars. Almost no one uses helicopters, right? So quantum computers sort of like in this analogy, that like helicopter is a great analogy because only very special applications, like even though a helicopter can go faster at a lot of things, like you don't really want to use it for most, like you can't really use it for most things. You just use it for the things where it's good at, like going over mountains or something, or going across traffic in Islamabad when so you have the mic there, if you can.
Just to follow on the previous question, if this is only going to be used for encryption and it's going to be a super encryption, I don't think it's going to appeal to the common people or common world. It will probably just appeal to the people who will probably do research at universities and maybe to very large companies. Until this has a commercial appeal to it, people will not donate money for research. Universities will not get any funds for research, and therefore this will probably die its own death. So until there is a commercial appeal.
But I told you the commercial application. Everything we do in the information, everything you do on the internet, every website you visit, in fact every website, pretty much like 95% of the websites you visit on your computer today use encryption. If somebody builds quantum computers, they can, like when you go to and log into your bank account website, somebody will come in, like if the US builds a quantum computer tomorrow, like a big one, they will come in and steal your money. Like they will steal your money, like they would have the capability of doing that. Or if you were like a spy or something, they would be able to read your communications. Like they will impact normal people, even though some people will use it. Like it's like a weapon that some people can use to impact everyone in society. So the reason for use, like everybody has to be concerned. Like does that make sense?
Yeah, you said to us before that you're attempting to scare us. You're scared us sufficiently. It's all right. Yeah, that's fine. Well, my direction is the other direction. Now, if we do not have it embedded in the normal life or social civilized life, the acceptance of this fact that it's only going to be used for digital application, encryption, cryptography, and so that your email is not attacked, for instance, or money is not stolen from the bank.
Right.
That's one part. But until it goes into something like data mining, for instance, or I understand that there will be simulation for the drug.
Yeah, absolutely.
That's fine. But there should be a little bit more impact on the application, on the commercial.
Well, I mean, I can't make up an application when it doesn't exist. So obviously, like the analogy of this is that in daily people's life, you will not, in like 10 years, you won't have a quantum computer at home on which you will, browse the internet. That is not going to happen. It's just going to be used in commercial sort of.
There is one example in which you're able to actually log on to a quantum computer online.
That's just for fun.
That's just for fun, but still.
And research. Sure, you can learn. Like as an educational tool, yes, absolutely, you should be doing that. So I think there's a question behind you, if you.
Thank you. So my question was that the post-quantum algorithms you were talking about early.
Right. You can keep talking. I'm listening.
So, yeah, that one. So no, the other one.
These are the post-quantums that are still not used, and
I'm sorry.
These are the ones that we use today.
The quantum key.
Oh, quantum key distribution. Yeah.
So, is it inspired from the Young's double-slit experiment in physics, which is?
Not really.
Because
you see the slits. I know you see the slits, but not really because they're usually only one slit at a time, not two slits. It's the double-slit experiment. This is like usually you have just one slit. So
okay.
Yeah.
So there was another.
Yeah.
So can we? What is the application of quantum computer in blockchain?
In quantum computers in
blockchain. Blockchain.
Blockchain. Well, so not quantum computers, but there are other. Like I've not talked about other applications of quantum devices that you can build. So people have thought about doing quantum money, like this electronic money, this quantum money where if I want to, in the blockchain, you send this message to everyone when you want to transfer money. Like if I want to send you money, I tell everyone that I sent you money. That's how it's recorded in the blockchain. So in fact, there's a quantum money proposal from all the way back from the 1970s. Before anyone thought of quantum computers, before anyone thought of quantum key distribution, there had been a proposal on how to use quantum technologies to build money. So there has been there. The blockchain itself, people have thought about reducing the energy consumption of the blockchain, which is the big problem with proof of work, with using some sort of, like everybody owns this small quantum device that does something like proof of work but doesn't take as much energy. I haven't read those papers, like there are a bunch, but I haven't read them, so I don't know how, like if they're really, like there's something there.
Okay, one more thing, sorry for that. So you said they are almost unhackable, even if you have a quantum computer, right? So you do know, obviously you know about that quantum computer works on qubits.
Right.
So what if we increase the amount of qubits on a
it doesn't matter. So there's, so when I drew this thing, here we are talking about breaking things and stuff like that, right? So the security here is sort of against it's what in the what do you study? Like what do you do?
Computer science integration.
Okay. So you understand, like there's something called computational security and there's something called information theoretic security. So computational security is like if your enemy has a computer which is maximum this size, then my code is secure. Okay, that is what computational security says. Information theoretic security says nothing about says my enemy can do whatever they want to do. They will not be able to hack my code. And the quantum key distribution is sort of that information theoretically secure code. It doesn't matter what, like there's no computation that you can possibly do to, it's not about fast or slow, there's no computation that exists to sort of gain the information.
Thank you.
So I just wanted to ask, so I was not here in the initial half an hour,
sure.
But I just wanted to ask, how does the quantum computer gain its power, its speed? So is it the parallel processing? Is it the transmission of information or protons? Or is it?
So I had this comic, there's this whole series of comics called The Talk, which talks about a lot of these things. It says theoretically, the important thing for you to understand is quantum computing is not just a matter of trying all the answers in parallel, which is the answer to your first question. Like it's sort of in a very vague way, yes, you are sort of trying all the answers in parallel, but that's not what really happening. There's a lot of other things that go on. I don't think it's like you have to sort of give me more time. Like it would be like at least a half an hour talk.
Primarily, you're saying that it's more of doing things in parallel. If I just
not really. I don't really want to say that. It's not quite correct, so I don't want to say it.
And are you using the term quantum computing to refer both to quantum hardware and software, or let's say if there is a software today, can it run on a quantum computer, or that requires a separate set of coding?
So a quantum computer can do everything that a classical computer can do. Like you can run the same code that works for a classical computer. It's like you sort of, if you compile it correctly, you can run it on a quantum computer. It doesn't help you at all. It runs just as slow or just as fast as a classical computer. But there are certain algorithms or codes that you can run specifically for quantum software that work specifically on quantum computers. You can't run them on classical computers. That obviously then help you in doing things faster on the quantum computer.
Okay, thanks.
Is the software fundamentally different?
Absolutely, it's completely different. Like people have these completely different languages, completely different compilers, a very, very active area of research.
Yeah, so you gave the helicopter and the car analogy, but when classical computers started out, nobody ever predicted that they would be in every phone, in every microprocessor, even in a digital clock or everywhere.
Right.
So I mean, we can't really just say that they're never going to get there. We don't know what sort of possibilities there might.
Sure, absolutely. I mean, I'm open to the possibility it might happen.
Yeah.
But I mean, think about it. In the 1930s, everybody was multiplying and adding numbers and factorizing numbers, whatever, when they were doing their business calculations or, just balancing their house accounts. So a computer was sort of like, the first applications, like widespread applications of computers were like word processing in offices and stuff. That's how, like, classic computer. So people were already doing those things on papers. They just started using the computer to do these things faster. But you sort of have to, like as this gentleman said, there has to be some sort of commercial application that, like you have to envision. Maybe there is. Up till now, we don't see it. So I won't say it.
But with quantum computers, the software or the language that we're talking about is fundamentally different and has sort of a completely different logic or counterintuitive sort of way of thinking about things. So that new way of thinking about things and we can possibly ask questions that we couldn't even ask before.
Absolutely, absolutely. I'm inspired by your youth and your optimism.
Okay.
Yes. My question is a little out there.
Sure.
But can quantum computing help solve the theory of everything?
Maybe, maybe not. Like, so when we do when I talked about the simulation of atoms, molecules, like obviously you can simulate other things, like you can simulate quantum field theories and stuff. So a lot of problem when we do as physicists, when we work on trying to understand like physical theories, a big bottleneck is that when we try to simulate them to sort of understand how the theory, what sort of predictions. Sometimes we can't make the prediction because it's so complicated that we can't even make the prediction. But it might be possible that for some theories it's very hard to make the prediction on a classical computer, but easy to do on a quantum computer. So then if we make those predictions, then it sort of helps the physicists understand, and then that might help the aid, like as a calculation tool, it might aid, sort of help move things along faster.
Exactly, because this is the problem, that quantum physics and relativistic physics are two different branches of physics. So like that's the problem with theory of everything, solving it, is that they are two different strands of physics.
Sure.
So, and there's a problem in sort of them coming together and then having us having this final theory of everything that Einstein also worked on till like his last dying minute, and he wasn't able to get there.
Sure.
So is the two of them?
Sure, absolutely. I mean, it might not. Like, actually, one of the things. So, one of the disappointments of this result that we had, I lost it. This one, breaking news, where it's sort of a disappointment also, because it's a sort of confirmation that quantum theory is correct. If people had kept trying, and like there are obviously people out there who think quantum computers are actually not possible, and like there would be something that would stop us from building the quantum computer and doing these calculations faster. And if it did happen, that's a very interesting possibility, because that means that quantum theory is wrong, and then that means we can think of theories that are like quantum theory but do not allow quantum computers to exist, and that would be sort of a help. So it's sort of a disappointment, because sort of every time your theory gets confirmed, then you don't know where to look for the next theory.
Exactly.
Hi. So my question is that since there's established proof or somewhat proof that a quantum computer has been made, so after a post-cryptic apocalyptic era, whatever that might come, or if it comes, how do you convince people to shift to quantum computing based cryptographic methods? Because humans are greedy.
So let's talk about this. So the first option is post-quantum crypto. You have to do absolutely nothing. Well, like the world will automatically, people are already talking about it. The emails in my inbox, the mailing list, where people are discussing how to do this and what sort of things to do. It's like it automatically. You never noticed when it will just be an update to your software on your browser or whatever that will upgrade this, and you don't have to do anything. Obviously, as Pakistanis, that means we have absolutely zero input in how the world tries to do it, and other countries might do it in a way that might hurt Pakistan's future. The other way of doing it, so whichever side, like quantum key distribution, obviously this requires money and time and effort and expertise, and I mean we can do it as a society if we agree on doing it and we sort of invest money in it. I mean, but if we don't, then we don't, and then
end of everything.
Yeah, it could be. Like, depends on whether post-quantum crypto is breakable by quantum computers or not. We don't know.
Thank you.
There are questions here, there's questions there. Maybe he can ask a question because you've asked before.
Well, you said that quantum computers are pretty fast in solving given problems, okay? So is there any possibility in future that quantum computers can actually predict things? Like if they can, then they are very vital in artificial intelligence where models are trained to predict data. Is there any possibility that quantum computing can predict the outcome of any stuff?
Not as far as you understand. Not really. Like, not really. Like there might be minor speed ups, nothing groundbreaking. Like as far as we understand, like no.
like we give it 30% of our data and then we want it to predict the 70% of the rest of the data.
So there's machine learning applications, as I mentioned. There was this whole slide about maybe do machine learning optimization. Sure. So we might be able to do machine learning on the quantum computer that is better and faster than the classical computer. But every machine learning quantum algorithm that has been proposed has been shot down. So it's sort of like I don't know, like, but it's a possibility. There was a question there, and okay.
So what is at the core of a quantum computer? Like for a traditional computer, there are semiconductors which are...
Sure. So there are lots of different ways of building a quantum computer. The one that Google made, or the one that IBM makes, this is the IBM quantum computer. It looks big, but most of it is cooling devices. Like most of it is cooling. What you have is somewhere a chip, somewhere inside, like a really tiny chip, and it's what's called superconducting qubits. So there's sort of superconducting currents flowing around, and they're really small, not small, as small as a transistor. Actually, they're fairly big by transistor standards. They are so transistors are on the order of nanometers these days, right? 10 nanometer, 20 nanometer, things like that. But superconductor qubits, each qubit is on the order of something like micrometers, or well, sub-micrometers, like 10 to the 7 meters, something like that. So 1/10 of a micrometer, something like that. So they're that big. They're just these currents that flow around, and in a very particular way. It's superconducting because it's super cooled, so there's no disturbance in the qubit. That's one way of doing it. Obviously, you can build quantum computers using photons. You can build them using ions. You can build them using atoms. You can build them using a bunch of other ways that, you know.
So currently, how many x is the quantum computer faster than, so whatever is thought of a...
So at useful things, absolutely zero. Like quantum computers are much slower at useful things right now today. It's just prototype phase.
But let's say for cryptography?
Absolutely zero. There's no, like, it's completely slow. It's like really these baby things that people play with. Like for useless things, which is what the Google result is about, the problem is actually very useless. Like they calculate this random probability distribution really fast. But it is something like, it's sort of the contrived problem that classical computers cannot solve fast. Quantum computers, their quantum computer can. But the useful part will come in about, so my guess is between 5 to 15 years. Like that's sort of the timeline that a lot of people predict.
But how much faster would be the speed? I'm asking because...
So a lot of faster. So at the things like breaking encryption, it will be billions of times faster or something like that. So a classical computer, like all the computing power in the world might take like 1 billion years. A quantum computer might do it in a few minutes or a few hours or something like that.
Okay.
So,
and is there some kind of a Moore's law for quantum computers as well? Like
sure, there has been a very but there are so many different technologies that's sort of hard to graph these things on a thing and sort of see that trend. But roughly speaking, yes, sort of it has been going fast. Like things are becoming smaller and bigger and so on at roughly the same pace. There's a question there.
So I remember reading up on the Chinese state announcing last year that they successfully communicated from a ground station a message using to the satellite, and I just wanted to confirm if they were using the same framework as the quantum key distribution. Was it something else?
So I think that was not quantum key distribution, that was quantum teleportation, if I remember correctly. Which is sort of very similar. Like if you can do quantum teleportation, you can also do quantum key distribution. In fact, quantum teleportation is much harder. So what they did was, like for people who don't know, they launched a satellite, and then from one city in China, they beamed the signal up to the satellite, and then that satellite sort of bounced that signal. So it was one photon from one city in China went all the way up to the satellite, got bounced off the satellite, went all the way down to the other city and got detected. And they did this like hundreds of thousands of times to sort of do the computation that, or process their physical experiment that they were doing. So imagine like one photon, like, you know, like this light is sending out 10 to the 23 photons or something every second. So something on that order. They were able to send one photon, you know, hundreds of kilometers.
So do you think it was an important threshold to cross?
It was a very important threshold. It was a big threshold, yeah.
With this new technology, quantum computing and all, with Pakistan, the problem is this, that we are always playing catch up.
Right.
We're in everything, we were at 3G, the world was at 5G and 6G, and that's how it's happening. Now with quantum computing as well, that is exactly what will happen.
Absolutely.
So what can't we do this, that we piggyback on China's progress in this field, and because China is a friend, and maybe we can, have a technology transfer and cut short the time that we can get there, because otherwise so we will always be playing catch up 10-15 years behind the world and everything.
Sure, absolutely. So China has been inviting graduate students from Pakistan for the past few years. Obviously people had been going all in the past too, but in the past 20 years China has invested a lot in the universities, and they want people from abroad to come in and study and teach at quantum at these universities and do research. So a lot of Pakistani students are doing research. I know people like my supervisor, in fact, is Canadian, like my PhD supervisor, but he had a position in China for 10 months a year. He was getting paid as much in China as he was for the 10 weeks. Sorry, he had to be in China for 10 weeks every year. He was getting paid for that 10 weeks as much as he was being paid in Canada for the entire year. And he had students, Pakistani students in China, who were sort of working on this quantum computing stuff in China for this Canadian prof in China. It was this international collaboration. So absolutely, it's possible. These people will train there and they'll come back. So that will happen.
Great, because that is the way to cut it short and get to that place where we need to.
Absolutely, politics is not you can't be isolated. You have to have friends and
instead of asking for $3 billion and $6 billion, we should ask them to have this technology transfer where we can eventually be earning $60 billion. We just think of 3 billion and 2 billion and 1 billion.
Sure, absolutely. Absolutely. I totally agree. More questions, even though we should stop at some point, because I'm sure some people do have to leave.
Just the flip side of that argument would be that some of these state secrets and things like these advanced research concepts, although the state would definitely want to encourage at the lower level, but for example, the quantum teleportation that we're talking about is pretty sure that China would be pretty guarded about.
Absolutely. I think if there are no other questions, I think we can close the floor now. Thank you all for coming, and I hope that